Wow, hello guys, welcome to my channel. Especially welcome you all to Master Builders Online Academy. You're welcome, you're welcome, you're welcome. Once again, I appreciate every one of you who are subscribers to this channel. Thank you for subscribing to our channels, and then thank you for liking our videos, watching our videos, recommending our videos, and then leaving positive comments at the comment section. It matters to us, and then we are so excited to have people like you coming to our channel to watch and then to learn content from us. We so much appreciate everything that you do on this channel. Also, so guys, without wasting much of your time, I'm actually here now so I can teach you some basic problems again in engineering thermodynamics. Remember, here on this channel, we are actually problem solvers. We find easiest way to always demystify complex engineering problem. So without further ado, let's just dive into this question. All right, now as you can see on the screen, we have that a system undergoes a cycle. Don't forget, a cycle composed of 4 processes. What are the processes? Process 1 to 2, process 2 to 3, process 3 to 4, and then process 4 back to 1. Now look at something amazing here. If you check 1 to 2, 2 to 3, and then 3 to 4, but we now have 4 back to 1. That means something will happen to the internal energy at that last point, because it is now from final back to initial. Oh, you understand the condition? Now that is clear. Now we now have the values here in tabular form, and then the energy transferred are tabulated as shown. We have processes 1 to 2, 2 to 3, 3 to 4, and then 4 back to 1. Then we have the heat flow, which is Q, and then in kilojoule per minute, and then the value are given for all the processes. So as you can see now, the heat for all the processes are given, but the work done for process 1 to 2 is given, but process 2 to 3 and 3 to 4 they are missing, and then 4 back to 1 is given. Then we will check under the internal energy. This is not changing the internal energy, it's just changing the internal energy that we have there, internal energy. We find out that the value for the first process is missing, and then the value for the second process is given. The value for the last 2 processes are given. Are you there? So now let's look at what the question required us to do. According to the examiner or the author, we are actually asked to complete the table, meaning fill in the values for the missing parameters. So in order to make this guy easy for us, can you see it? It means that for process 1 to 2, we should find U1 here. Can you see it? And then for this process 2, we should find W2. Can you see it? And in this process, we are finding W3 and then U3. And then in this process, we are finding U4. So let's list it this way. So these are the 5 parameters that are missing here. Take for instance, this question is to come in as an objective question. Automatically, as you have it now, you have this table to answer up to 6 different questions. Because only number A, which you are asked to complete the table, you will find U1, U3, and U4. 3 there, the work done, you find 2. Then when you now come to the last one, which is question number B, we are now asked to determine the rate of work done in horsepower. Determine the rate of work done in horsepower. And don't forget that the rate of work done is the same thing as power, because power is energy extended or work done per time. Are you there? So, and more also, as you can see, the values that are already given, the values are given in terms of energy per seconds, right? So all we just need to do now is to start taking these processes one after the other and then begin to obtain the unknown parameters. I hope you understand what we have so far. So we have our solution here, and then we will start from process 1. Can you see this? For process 1 to 2. All right, so we are going to make this very short in order not to start writing long sentences. What are we given in this process? What are we given? In this process, what we are given is Q1 to 2 is given as 420 kilojoule per minute. And then under this process again, we are given work done between 1 to 2 is given as 148 kilojoule again per minute. All right, so this is what we have. Now, what is missing here is internal energy. So internal energy between 1 to 2, which is same thing as our change in internal energy, is unknown. So all we just need to do from here is to record the equation of first law of thermodynamics based on these three parameters that we have here. So you just recall that Q minus W is equal to change in internal energy. So in order for us to suit this equation to this process that we are in, we can actually call this as Q1 to 2 minus W1 to 2 is equal to U1. Remember, we call this actually as U1, right? That's what is missing there. We call this as U1. So that's what we have there. So we just put in this. Then we are looking for U1, right? So we can make U1 instead of formula. U1 is equal to Q1 to 2 minus W1 to 2. So we just put out the value. The value for this is 420 minus the value of work done is 148. And then if we remove 148 from 240, we have this as 272 kilojoule per minute. Hope you have gotten this, all right? And then the value is positive. It's as simple as that. So we have been able to complete the first process. Now, if we come to the second process, which is process 2 to 3, as you can see here now, process 2 to 3, we are given heat. We are not given work done, but we are given internal energy. So let's put this down. Process 2 to 3. Now, for process 2 to 3, again, we are given Q2 to 3, and then we are given W2 to 3 as W2, which is not known. But when we come to the table, the value for Q2 is given as 210, as you can see here, right? So we have this as 210 kilojoule per minute. Are you there? So now what next? As we look at this process again, we were given 314 as the value for change in internal energy, right? So we can actually say that change in internal energy between 2 to 3, which we actually call U3, is equal to what value? Is equal to 314 kilojoule per minute. Are you there? Again, all we simply need to do is to remember the first law equation for thermodynamics. Are you there? So recall that Q minus W is equal to change in internal energy. And what is actually missing here now is work done, right? But if we want to suit this equation to this particular process, we can actually call this Q from 2 to 3 minus W from 2 to 3 is equals to change in energy also from 2 to 3. So in putting in the parameters or making W2 the surgery of formula, we have 2 to 3 would have given us Q2 to 3 minus change in internal energy 2 to 3. And then if we finally put this to its least level, this becomes W2 is equal to Q2, and then this minus U2. Finish like this. So all we just need to do now is to put in the value for this guy. We're given 210, and then for this other guy we're given 314. All we just need to do now is to include this into our calculator by subtracting 314 from 210, and if we do that, we have negative 104 kilojoule per minute. So this is the work done on this process. And then assuming we are interested in what type of work is this is work done on the system because the result is negative, right? So this is work done on the system and not by the system. Okay, so we are done with that process. As long as we are able to complete this row now, we are done with this. Then the next thing we're gonna do is to come to process 3. But now, one of the problems that we'll have with process 3 is that in process 3, we only have one known value and then 2 unknown. And remember, mathematically, it is not possible for you to find 2 unknowns from one equation. But if we come to process 4, we'll find out that we have 2 known and 1 unknown. So what we are going to do now is to first of all find U4. I hope you can see it. Find U4 because in the fourth process, only U4 is unknown. But in the third process, which is 2 to 4, we don't know W3 and then we don't know U3. And both value on this row will be taken from one equation. So because of that, we will jump this process first and go to process 4 to 1. I hope you understand the reason why we are doing this. All right. For process 4 to 1. Are you there? So this is it. Now for process 4 to 1, if we come up to the question here, we'll find out that Q, which is work done, is 0. This Q is 0, which is heat, and then work done is 74. So we'll just list the parameters. Are you with me? All right, so Q from 4 to 1 is given as Q4, and that value is equivalent to 0. Then W4 to 1, we can call it W4, and then the value is given as 74 kilojoule per minute. I hope you can see it. Just look at it here. This is it here. This is it here. All right, so this is it. This is it here, 74, and then this is what we are looking for. All right, so if we progress to internal energy between these 2 points, so we have change in internal energy between 4 to 1. This is actually U4. Are we there? And then this is unknown. So you see now that from here we can actually find U4. And now in order to find U4, what do? All we simply need to do, guys, is to ensure that we state the first law of thermodynamics equation. And then you say recall Q minus W is equal to change in internal energy. So in order not to waste much of our time, guys, this is exactly the same thing as Q4 minus W4 all equal to U4. Okay? And then we are looking for U4, so U4 is automatically equal to Q4 minus W4. And then what is Q4? Q4 is 0. Minus W4 is 74. And then when we simplify this, we have our final answer to be negative 74 kilojoule per minute. So this is the answer to this very question, as you can see. I hope you can see it now. This is the answer to this question, and it's so simple. So we now come back to process 3 to 4, where we will now obtain W3 and then U3. Are you here? When we find W3 and then U3. Okay, now let's take this process. Okay, now guys, for process 3 to 4. All right, so this is where we are. Process 3 to 4. In this process, as we can see from the question, all right, so for this process 3 to 4, this is actually Q3 to 4 is equal to Q3. And Q3 is given as negative 210 kilojoule per minute. And then again, work done between 3 to 4 is the same thing as W3. And then this is unknown. Why change in internal energy between 3 to 4 is U3, and this is unknown. All we just need to do now is to recall the equation for thermodynamics law, right? And then which is for law 1. And we then have recall that Q minus U, W is equal to change in U. And then to suit this particular equation, we can simply just go ahead and call this 3, then minus W3 is equals to U3. Now, from where we are now, we are supposed to substitute or make one of these unknown the Sawyer formula. But because we do not know W3, we do not know U3, and then we are quickly going to call this one any equation. Let's label this as equation 1, okay? Because that's the only equation we are having so far. So now there is a law that will help us solve this problem. Let's go back to the beginning of this question. We are told that a system undergoes a cycle composed of 4 processes, a cycle. So how do we get to know that it's a cycle? It begins from 1 and then ends back at 1. Are you there? It starts with 1 and the process also ended in 1. 1 to 2, 2 to 3, 3 to 4, and then 4 back to 1. So because of this process, and then it's actually a cycle. So whether this cycle is here or not, as long as you have this chain like this as a closed loop, all you just need to do is that the sum of all the internal energies will actually be equal to 0 for any thermodynamic cycle. Are we there? So all we just need to do is that we need to first of all find U3. To find U3 or U3 back to 4, this is the process. All you just need to do is to record that cyclic integral of du, which is summation of all the work, all the internal energies is equal to 0. Are you there? The summation of all the internal energies is equal to 0, which automatically means that U1 plus U2 plus U3 plus U4 is equal to 0. And of course, we already know U1, we know U2, we know U4, right? We have calculated for all of these values. As you can see it here now, U1 is calculated to be 272, U2 was given as 314, and U4 has been calculated as negative 74. All we just need to do now is to put in the values, and then we'll make U3 the subject of formula. So automatically this is 272 plus the value of this other guy is 314 plus U3, then plus the value of this is minus 74, all equal to 0. So as you can see now, only U3 is now the unknown parameter here. So we have 272 plus 314 plus U3 minus 72, all equal to 0. And then by the time we add all of these values together, this would have given us U2, U3, plus, if you add 272 to 314, we'll have 586 minus 72, all equal to 0. Then U3 will give us plus 512 if we remove 72 from 586. And then all we just need to do is to make U3 the zero formula. And if we do that, we simply take 512 to the other side, and then this becomes negative 512 kilojoule per minute. So we have been able to obtain the value for this guy. You see, it's very, very simple. Now that we have gotten U3, we know U3, we know Q3, we can now find W3. I hope you can see that there. From equation 1 above, recall that Q3 minus W3 is equal to U3. So I'm looking for W3. So if I make W3 zero formula, I'm going to have Q3 minus U3. We already know Q3 in that level, and that Q3 at that level is negative 210, right? As you can see it here, or as you can see it at this point. Look at where we extracted the parameter. So it's negative 210. And then the value for the other guy is negative 512. All right. So let me just state it so that it will be clear for us again, where Q3 is equals to negative 210 kilojoule per minute. And then U3 is equal to negative 512 kilojoule per minute. And then we can now put in the value so we get our W3. I hope this is actually educating, right? So this is W3 is equal to, just put in the values. This is minus 210 minus 512. So first of all is to clear off the bracket. We have minus 210 minus multiplied by minus turns this guy to plus, and then we have 512. Now minus 210 plus 512 will give us 302 kilojoule per minute. So guys, we have been able to get the values that completes this whole table. So we have been able to answer the A part of this question, right? We have been able to answer the A part. I've been able to answer the A part. So the B part of it now, we are now asked to determine the rate of work in horsepower. The rate of work in horsepower. The rate of work in horsepower. So for us to be able to find the rate of work here, we are going to sum up the heat. All right, so all the summation of all the heat here is what will give us the rate of work, not the work done, not the work done. The rate of work is obtained from the summation of all the heat. All right, so we move down. So this is the B part, and then we are asked to find rate of work done. All right, which is actually power. All right, like I just mentioned now, to obtain the rate of work done, we are going to sum up all the heats. So just recall that cyclic, we use this in one of the equations problem we solved before, integral of the Q is equal to cyclic integral of the W. All right, so this is it. Now it's very, very simple. So all we just need to do now is to what? Get only the net heat transferred. So the cyclic. All right, so now at this point where we are, all we just need to do is to make sure we put this guy in its place. And what do? Work done here is now equal to Q1 plus Q2 plus Q3 then plus Q4. And then what is Q1? Q1 was given as 420, then Q2 was given as 210, and then Q3 was given as negative 210, and then Q4 is given as 0. So by the time we simplify this now, this gives us this plus 210, then minus 210 plus 0. Automatically, when we remove 210 from 210, we have 0. Then the work done here is 420 kilojoule per minute. Now, this is not the answer, but this is actually the work done or the rate of work done, okay? Which is the rate of work done. This is actually the rate of work done. So you can actually make use of P or just use the normal W, all right? So we have thereby power P is equals to what? W. Why? Because we have the same value. The unit is the unit of power. So we have this per minute. But as we can see from the question, look at it very clearly. You will find out that from the question, determine the rate of work, not just rate of work, but the unit to leave your answer is specified. And what unit? Leave your unit in horsepower. You can see it now on red. You leave the unit in horsepower. So how do we now leave this unit in horsepower? We now have to convert the answer that we had before so that it will be easier for us. So first thing is that to be able to convert this to horsepower, we first of all need to convert this power to joule per seconds. As we can see now, we have it as joule per minute. So we have, but 1 minute is equal to 60 seconds. Are you there? And then 1 kilo is equal to 10 raised to the power of 3. All we need to do now is to first of all reduce this unit from kilojoule per minute to joule per seconds. Are you with me? To joule per second. So we have power which is rate of work, P, is equal to 420 multiplied by 10 raised to the power of 3 joule. We just remove kilo by 10 raised to the power of 3, then per minute. 1 minute means 60 sec. Guys, I hope you are seeing what I'm doing here. So by extension, this is equivalent to 420,000 joule all over 60 sec. Now, when we divide 420,000 joule by 60 seconds, our final answer here, P, at this level becomes 7,000 joules per second. This is where we are now. Now, it is now very, very easy for us to convert this to watt, right? And then we understand that 1 joule per second is equal to 1 watt. So this is equivalent to 7,000 watts. As simple as this. Then we can convert this to kilo. Divide this by 1,000. This will give us 7.0 kilowatt. We have gotten the value in kilowatt, but not yet in horsepower. So we now have the relationship between kilowatt and horsepower. Now recall that 1 kilowatt is equal to 0.745 horsepower. See now? So this is why we have to convert to joule per seconds, then from joule per seconds to joule per seconds to watt, and then from watt to kilowatt. So now we record that 1 kilowatt is equivalent to this, right? So what we just need to do now is to have that P is equal to 7.0 multiplied by 1 kilowatt by 1 kilowatt. This is what this represents, right? So this becomes 7.0 multiplied by what is 1 kilowatt? 0.745 horsepower. And then by the time we multiply out these guys, our final result, yes, the oga patapata of this solution is 5.215 horsepower. This is the final answer to this question. So we are asked to do all of these things that we just did. So guys, you find out that it is very, 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 very simple to solve thermodynamic problems in engineering thermodynamics, right? But one of the things is you really need to understand what you are doing and then what is required from you. So we're asked to complete this table, which we have completed. We're also asked to determine the rate of work, which is the same thing as power, in horsepower. Let the unit be in horsepower, and that is what we have just done through this process 1 to 2. We find U1, process 2 to 3. We find W2, process 3. Process 4 to 1, we find U4, and then process 3 to 4, we find U3, and then we find W3. And finally, we are able to find the rate of work done, which is power, and then cyclic summation of, for every cycle process, the sum of heat is always equal to the sum of work. And then in this case, we have all of this sum up. We have this in joule per minute. Like I said, the first thing you need to do is to convert this to joule per seconds. And 1 minute, as we have it here, we said that 1 minute is equal to what? 60 seconds. And then 1 kilo, again, is equal to 10 raised to the power of 3. Are you there? And then that's how we have it. And then we now substitute into the equation, reduce it to joule per seconds. 1 joule per seconds is equal to 1 watt. And then we just replace joule per seconds by watt. And then to convert to kilowatt, we divide the value, which is 7,000 by 1,000, and it's reduced to 7, which is same thing as 7.0 kilowatt. So to convert from kilowatt to horsepower, 1 kilowatt is equal to 0.745 horsepower, which is represented with HP. And then we have 7.0 times 1 kilowatt. That's what this represents. And then when we put in the value of 1 kilowatt and multiply out, this is the answer to this very question. So guys, as promised, I've been able to hold you by hand and walk you through the processes of solving these problems just as you have it here on the screen. So we love you so much. Thank you for watching. We love you guys. Please, if you are yet to subscribe to this channel, do consider subscribing to our channel and ensure you turn on the post notification bell for more exciting content. So guys, don't forget to like this video, share this video, and make your necessary comment. That is very, very important to us. Share your comment. Let us know your thoughts about this video. We love you guys. See you guys in the very next class. You can check the description of this video so you can access the next video and even the previous videos made on engineering thermodynamics. Thank you. See you guys in the next class.